Okay, good afternoon, everyone. My name is Mohammadreza Mehrabankoopaei, a PhD student at Tecnico di Milano and working on cold spray. And today I will talk about some predictive model of shape, a deposition shape of cold spray. So, okay, what is cold spray? It's a coating technology in which we accelerate fine metallic powder into supersonic regime using compressed gas. And upon collision with the substrate due to severe deformation, the powder starts to adhere to the substrate, and because of because everything happens under melting point, we can use this technique in even additive manufacturing realm, in repair and also welding. But one challenge in depositing thick deposition using cold spray is shape prediction, because if we consider the gas stream after exiting nozzle, we can see that most majority of the powder are concentrated along nozzle axis. So we will have a Gaussian-like deposition shape. Today I will talk about a 3D shape predictor model and also a fast surrogate to be integrated with an optimizer. So the analytical base that I use in my model is this PDE, in which which shows or represents the deposition growth through time. Here, A, D, E, and J are empirical constants and functions that needs to be determined from, and they change from one material to another one, from one process parameter set to another one. So conventionally, when researchers want to use this model, they need several experimental deposition shape to calibrate these constants. Here, A is a constant that is related to material and process parameters. DE represents the effect of the impact angle, and also J is a function that shows the shape of the particle. In general, we can define J as follow, a Gaussian-like function. Here, again, we have another constant, which is material and process parameter related, K2. So there are two challenges. The first, how to calibrate or find these constants, and the other one, how to solve this PDE for an arbitrary temporal and also spatial domain. To address the first one, we developed an inverse model that could extract all of these important constants from only one experimental deposition track. And for the next one, I have developed a forward model that gets the output of the inverse model and also the initial substrate geometry and also a nozzle movement and other parameters, and give you the final shape after spraying. So let's go to the result. The first one actually shows the evaluation of the inverse model. Here we used the same process parameters, same material, but depositing for different number of passes. And as you can see here, for both A, K2, and also the relative deposition efficiency of impact angle, it gives us almost the same, outputs showing the robustness of the inverse model. Next, we used those outputs to evaluate or predict the deposition shape of some experimental, deposition. We did that for pure copper and also a titanium alloy for different number of passes, different spraying angles, different spraying speeds, and also different track numbers. And by track, I mean two parallel spraying deposition. And also the forward model could be used for toolpath planning, such that because you can see everything in real time, and so you can use the model to plan the nozzle movement based on your target. However, this is not a shape control tool because the input would be the nozzle movement. So we need somehow, in order to get to optimize the nozzle movement based on a final desired shape, we need to integrate this physical 3D model with an optimizer. But because this model is a little bit slow, so it takes a lot of time to optimize the nozzle movement. So here we decided to, instead of using the physical model, we will use a surrogate machine learning based model. Also because the main focus of my thesis is on welding, and most of the welding joints are shapes with constant cross sections. We downscale the model into 2D model. But okay, let's go to the next slide. Okay, for training the surrogate model, we need big data. To obtain big data, I developed another code which I call Morphos. Morphos here decide to combine different possible parameters or spraying parameters, as well as substrate geometry, and it creates a deposition based on those combination of parameters and substrate geometries. And also, okay, if the Morphos take fresh substrate, it creates the first class of data. If it takes a substrate from the database that has been sprayed once, it creates the second one, and so on. So the fifth class of data would be a fresh substrate that has been sprayed for 5 times. And then after producing or generating the data set, we used a different kind of model architecture, and these are the results of the trained the metrics and loss metrics and performance of different kind of architectures trained on 1 million instance data set, which has been generated by Morphos. And as you can see, we tried different kind of architectures, from very baseline simple neural networks to complex transformers. And as I expected, the best performance was for transformer, with a performance or error, mean absolute error, about 13 micron. And here we can see the difference between the prediction of the physical model and the surrogate model. And as you can see here, the surrogate model could almost capture the physical prediction. And also we evaluate the surrogate model with 2 benchmarks. Here, this is spraying a simple wall with corner compensation. And here, the surrogate model was about 30 times faster. And here, another example of filling a gap. And okay, the surrogate model was about 44 times faster. So the applications and potential of the surrogate model that we have now is, okay, the first one, at this stage, we can use the surrogate model for predicting deposition shape for applications that are linear, or they have a constant cross section, or even axisymmetric spraying. The next step that I'm going to do is to integrate this surrogate model with an optimizer, such that we input the desired target shape, and the optimizer would tell us the optimized nozzle movement. Then also we can upscale this 2D model, or this 2D surrogate model, into 3D, because we can approximate a 3D nozzle movement with several superposition of several linear movement with constant cross sections. And also, finally, the destination of this kind of jobs could be combining this intelligence with a digital twin of the robot, and we get the data from real-time monitoring of the shape and control the robot. And thank you very much. I would be happy to answer.